Okay, momentum and impulse. First question, can you have inertia sitting in your seat? Well, remember, inertia is based on how much mass you have, only your mass. It has nothing to do with motion. Okay, well, actually, I shouldn't say it has nothing to do with motion. Remember, Newton's first law, objects in motion tend to stay in motion, objects at rest tend to stay at rest. That's also called the law of inertia. But it's based on how much mass you have. It's not based on how fast you're going. It's not based on how much volume you take up. It's simply based upon your mass. So the next question is, do you have momentum? This is relative to the room, just like everything else would be, just sitting in your seat. Do you have momentum? Think about things that have a lot of momentum. A football player running. What about a car sitting still? Does it have momentum? Well, what is momentum then? What does momentum mean? Think about it this way. Which is harder to stop? A truck moving 30 miles per hour or a motorcycle moving 40 miles per hour? Explain why. The truck has more momentum than the motorcycle, even though it is moving slower. The truck has more inertia, but the motorcycle has more momentum. Momentum is a product of mass and velocity, not simply mass, whereas inertia is just a product of mass. So momentum, which is the lowercase p, is equal to mass times velocity. Momentum has both direction and magnitude, so it is a vector quantity. So what factors affect an object's momentum? Well, obviously, mass and velocity, right? What about force? Well, think about it. In order to get something moving or change its motion, in order to change its velocity, what do you have to add? A force, right? Well, is that done in an instant or does it take time? Well, it takes time. So think about it this way. When you push with the same force for twice the time, you impart twice the impulse and produce twice the change in momentum. So therefore, time does play a factor. The quantity of force times time interval is called impulse. So another way of thinking about it is impulse is equal to a change in momentum. So notice this is force times time is equal to a change in mass times velocity. And remember, your mass probably will not be changing. It's just your velocity. So how do you increase momentum then? Well, you have a greater change, or you have a greater impulse, right? So tell me how this person playing tennis could have a greater change in momentum of the tennis ball. I used to be a tennis coach, and whenever I was actually the assistant tennis coach, and it was kind of a joke. I was not good in tennis. I was really good in racquetball, and I thought that would make me fairly good in tennis. And I think I've talked to you guys about this before, but I used to play these guys that were really, really great, but had tiny arms, and I could out-arm wrestle them any day of the week. But whenever they were playing tennis against me, somehow they could make that ball go way faster than I could. So what were they doing different? Well, have you ever heard of follow-through when you're playing a sport? The reason why follow-through is so important is because that increases the time the ball is in contact with the tennis racket. Therefore, the force is acting over a greater amount of time. I had horrible follow-through. I would hit and pull back. I would hit and pull back, which a lot of times is what you need to do whenever you're playing racquetball, because you don't want to hit the wall and you don't want to hit the other person. You're playing in a more confined space. But with tennis, you want to get that tennis ball going as fast as you can and control it the best you can. So you hit and you follow through with it. And being honest, I wasn't that great a racquetball player either, but I was definitely a better racquetball player than a tennis player. Okay, so this not only affects tennis, but it also affects a whole lot of other sports. For instance, golf. The longer the golf club is in contact with the golf ball means the greater the change in momentum. This works well with baseball, tennis, soccer, football, so many other sports. And that's one reason why your coaches are always on you about follow-through. It's because they know that they can take a little person, a little guy with small arms, or whoever it is, with smaller arms, and they could have the same effect as a big guy that doesn't understand how to have follow-through. Now let's kind of change gears. Sometimes I like to talk about cars. If you had a choice between wrecking into a haystack or a brick wall, which would you choose and why? Now let's think about this. Again, look at this formula right here. Force times time equals a change in momentum. Remember, your velocity, your final velocity is going to be 0. Your mass isn't going to change. So this over here is set. The only thing that you're going to change is your force and your time. If you hit a brick wall, you have to undergo a large amount of force. This gets larger, but this gets smaller. If you hit a haystack, the time gets larger to take to stop, but the force gets smaller. Which one would you rather have? You'd rather have the haystack, right? Because if you're in a wreck, you don't want to have a huge impulse. That's a bad thing. Your change in momentum will be the same, but it's the impulse that will make the difference. So the change in momentum must be the same for both situations. There is a trade-out between force and time. The haystack takes longer to slow the car down, so there is less force involved. And of course, you can see how they've made the letters bigger to make you understand. Here you have a greater change. You have the same change in velocity for both of them, but here with the wall, it's a larger force over a smaller time. Here with the haystack, it's a smaller force over a larger time. Same change in momentum, though. Same exact change in momentum. So what other applications has this relationship been applied to? Well, what about boxing? Have you ever heard of rolling with the punches? Well, the idea is that if you just stand there and take it, you're going to, as in with this guy, he's just standing there taking it. It's going to have a small time, but a larger force. That's going to hurt your face worse. But if you move back, as in part A here, it's going to have a larger time and a smaller force. So which has the greater change in momentum? Catching a falling flower pot or catching it and throwing it back up again? Now this one you really have to think about. Would you rather have a flower pot hit you on the head and break around you? Or would you rather have the flower pot hit you on the head and bounce off of you? Well, catching it and throwing it up again does, because you have to not only change the velocity going to 0, but you also have to push it back up off your head. And this is what occurs whenever you have something bouncing. So there's a greater change in momentum. So that one will actually hurt you more. Getting something to bounce off somebody's head actually hurts them more than having something break. And this is one reason why you don't see bottles being broken off people's heads in movies. Notice they always break. They never bounce off their head, because if it bounces off their head, well, first of all, it's a special bottle and it's meant to break. I think they make them out of sugar, so they're not sharp and they still shatter. But if it were to bounce, which actually it's pretty hard to break a bottle if you're hitting something like a head, it's going to hurt them really, really bad. It's equivalent to being hit by a steel baseball bat, actually. So let's move on. So what hurts more than a flower pot that falls and hits you on the head, then breaks and falls on the ground, or the one that hits you on the head and bounces back up? Well, the one that bounces, it produces as much as twice as much force on your head. The impulse required to bring an object to a stop and then to throw it back again is greater than the impulse required merely to bring the object to a stop. This is what happens when something bounces. So this has been utilized with the Pelton wheel. This is a curved blade on a type of water wheel. I believe they have one of these, or at least something very similar to this, in the Frontier, I think it's called the Frontier Town, or across from the zoo. I don't remember what that's called, but they actually have a Pelton wheel up there, and you can see it. What happens is, rather than the water just hitting and splashing and setting in there and pulling the wheel down, it bounces, imparting more impulse to the wheel as it turns. Pretty cool idea. And actually, if you look on some propellers, you'll see that they're curved a little bit, and it gives that bouncing effect as well. It's, again, pretty neat. Okay, well, we're going to stop here and let you guys kind of take your breath. That's a lot of notes all at one time, and I hope you have learned something.